All right, so our next three presentations are jointly coordinated with the MEX network, which stands for Multi-Hazard Engineering Collaboratory for Hypersimulation, and which is also led by Dr. Shirley Dyke, the presenter of the third talk today, and the MEX Committee on Fluid Structure Interaction, which I'm chairing. The first presentation is by Dr. Tengu, Associate Professor in the Civil Structural and Environmental Engineering at the University at Buffalo. And Dr. Wu's talk is titled A Cyber-Physical System for Fluid Structure Interaction Wind Engineering Application. Teng, are you ready to share your screen?
Yes, thank you. Let me share my screen first. Okay. Can you see my screen?
Yes. Can you play the full screen mode, maybe?
This is it's not a full mode.
No. Yeah, now it's full mode. Yeah, perfect. Thank you.
Oh, it has some delay.
Yeah, it's all yours. Thank you.
Okay. Thanks, Emil, for the introduction. Hello, everyone. My name is Teng Wu. So I'm an associate professor at the University of Buffalo in the civil engineering program. And my background is wind engineering. So today I would like to talk a cyber-physical system for its application in wind engineering. So we have extreme winds, and the extreme winds, our structure will have an intensive response that including the vertical structure like tall building, low-rise building, and chimney, and also horizontal structure like bridges, and also the inclined structure like stay cables. So you actually can see the stay cables actually vibrate very intensively. So we want to avoid this phenomena and the winds. So we want to understand all those structure behavior and the winds, and also we want to accurately simulate all those phenomena so that we can mitigate if the response if necessary. So to simulate all those phenomena and winds, and the first approach with the computer. So essentially, we can put everything in computer. It's like the similar concept like a digital twin. Nowadays, very popular in the manufacturing industry. So, for example, we simulated this tornado event, and we put the structure here. The structure is, you can see, is the high-speed train in the tornado, and we also can simulate the downburst. Actually, it's a moving downburst, and if we examine the video more closely, you can see here there is a long span bridge. So we can put both wind and structure in the computer. But the problem is the computational demand is still too high for, even for nowadays. We have all kind of high performance computers. For example, for this tornado simulation, the mesh, the one case we have around 600 million mesh. So to accurately predict the aerodynamic force on the train. More importantly, actually, if you observe this bridge deck or the train structure, actually they are static, which means the structure is not a response. Unfortunately, if you see this figure, if structure starts to move, that will modify the wind surrounding the structure. And of course, then we'll have additional wind load. So if we put the structural response in this video, in this simulation, the computational demand will significantly increase, further increase. So it easily you use like several weeks to simulate just one scenario, one case. So to put everything in the computer in numerical world, we use the CFD to simulate the wind. We use the CSD to simulate the structure dynamics. And those CFD and the CSD, they are strong coupled. And the strong coupling is an issue to deal with. So summary, the CFD, CSD, and the flow structure interaction simulation numerical world is very promising, but probably the time is not ready yet. So the other way is we put everything in a physical world. That's use the physical modeling, use some scaling law and similarity rules. By the way, this is enveloped by Professor Scott in MIT. I forgot to add the credits. So this is the bridge model in the Tongji's University's wind tunnel. In addition to the issue, put everything in the lab in physical world, use the wind tunnel. In addition to the nanoslumber effects, which is very common to this kind of test because of a scaling issue. But some people think it's not that important for our civil engineering because the structure usually have a brown section. We still have several other issues we need to address. For example, the structural nonlinearity, because the model usually in wind tunnel is very small. We actually cannot capture the structural nonlinearity. And we even actually cannot capture the multiple modes for this bridge. And also, we cannot capture the area elastic nonlinearity. So if the response is too large, we want to mitigate the response. So we want to do the aerodynamic modification to modify the structure shape. But unfortunately, the automated fabrication of structure mode and related issues in the wind tunnel is not established yet, which means if we want to do the mitigation strategy, that will be very time consuming, labor cost. So logical thinking will be okay. The both numerical and physical world has some issues. Can we combine them to enhance our capacity to simulate wind-induced effects on structures? So the combination is a very natural and logical thinking. But the first question we need to answer is which part we put in the numerical world, which part we put in the physical world. So the first approach will be, let's put the wind in the numerical world. And so that's the dynamic load simulator. A number of researchers have used it to do some tests for wind mitigation and for floating wind turbine. But the issue to do this split is that if we put the wind in the computer, unfortunately, our understanding of wind-induced effects, that's the aerodynamics, is not perfect, or actually is far away from for understand this physical phenomenon. So, which means we will have a large error in the numerical part. So the other thinking will be, okay, let's put a structure in the computer because most of structure behavior we can accurately simulate in numerical world. So that's some people also did this. For example, MIT group used this kind of a concept to test the hydrodynamics load on a cylinder in the water tank. And also the Japanese research, Professor Kanda has used this kind of concept to investigate the wind effects on tall building, a simplified building model. This concept is actually very promising, but previous research actually the one thing we can improve is the control system. All those previous studies, the control system has been oversimplified. For example, the interaction between the actuator and the structure are not discussed in these studies. So on the other hand, we know in the earthquake engineering community, many technology has been advanced to adjust this control design and in the real-time hybrid simulation. So we think this is a very promising approach in wind engineering. We want to use the real-time hybrid simulation methodology to apply to the wind engineering. So the concept now is very clear. We have a skeleton, we call it, of a structure characterizing the dynamic property, which will be numerical simulating computer. And we also have a scheme of the structure characterize the aerodynamic property will physically model in the wind tunnel. And the skeleton will give the displacement to the scheme. And the scheme will give the aerodynamic and the aeroelastic force to the skeleton. And the interaction between skeleton and the scheme of your structure accomplished through a system consists of sensors and actuators and controllers. So for the scheme, in the physically in the wind tunnel, actually it has first the gust wind-induced aerodynamic force on this scheme. And also it will have the motion-induced aeroelastic force on the scheme. And those two forces should be hybrid or synchronized at each time step. So this is why we call the real-time aerodynamics hybrid simulation, because we want to use the word aerodynamics to cover both aeroelastic and aerodynamic considerations. So we want to implement this real-time aerodynamics hybrid simulation in our wind tunnel at UB. And to do this, we have developed a simple but enough supporting system to do some experiment work. So the problem formulation is straightforward. We have a physical scheme, a subsystem, measure the force to give to the virtual skeleton subsystem, and then we have a reference position, and we have a command to actuate, that's the controller design, and then apply the displacement to the physical system. That's as a loop. If based on this is a kind of conventional approach. If based on this approach to do the control design, we realized there are several popular issues we need to handle. First is the actuator will interact with the model. That's the structure control structure interaction. And also actuator not necessarily check a motion exactly. So we need a compensator. And also we need to carefully select the time integration scheme, especially if we have complex structure dynamics. And also there are some additional dynamics and errors from the sensors. So to avoid those, there are many techniques developed in this community to address these issues. But our understanding is there is for wind engine application, there is a dilemma or conflict here. So to have a good control design, we probably need to have very good understanding about the physical scheme subsystem. Because it put the disturbance to the actuator and the controller. And however, the reason we do this kind of real-time aerodynamics hybrid simulation is because we actually don't have a full understanding or good understanding on our physical scheme system. That's the structure aerodynamics. So that is kind of a dilemma we are facing. So to avoid all those issues, we are using a kind of a novel control design, which was developed by my colleague at UB, Professor Siva. It's a very simple and straightforward concept. Essentially, the design of a controller in the RTHS is to ensure the actuator with the controller to represent the virtual skeleton model. With the same input, we will have the same output. So that's it. That's the concept. And so based on this concept, we realized the design of control is completely decoupled from the physical subsystem. And no explicit tracking controller or compensator to make up for inexact trackers. And also there's no special role for a numerical integration scheme, except we just need one for implementation purpose. So if we have a bridge section model, and then in the equation of formation for the skeleton, the structure dynamics for this 3 degrees of freedom system is pretty straightforward. And there's parameters, and it can be represented in the state space. So the y over bar is the displacement transmitted from the skeleton to the scheme, the physical model. So if we use the actuator to replace this virtual model, and if we use we select the electron magnetic actuator, so we have equation of the coil, and we also have a relationship between the control input voltage and the current. So this system can also be represented in the state space. Y here is the actuator displacement. So the control design in state space term could be stated as for x equal to 0 and x over bar equal to 0. We need to find the u so that y equal to y over bar at each time instant. So since in the current stage we focus on this linear virtual skeleton system, so it will be very convenient to use the transfer function approach to illustrate this concept with a little bit more details. So we have these two systems, same input, we will want same output, so then the transfer function will have this equivalence, and then the linear controller will be expressed in this way. And of course, if we want to have this linear controller exist, we want the inverse of the HDU is meaningful. Also, we need to handle some issues during implementation in real time. That means the controller need to be stable and causal. So there are a number of strategies we have used to make sure this is guaranteed. And we want to highlight that although the virtual skeleton model here is linear, extension to a nonlinear virtual skeleton model will not involve much complexity. Actually, my colleague Professor has already applied this methodology in a nonlinear numerical model. So also, we want to note that there's no restriction on the behavior of a physical scheme model where the aerodynamic aeroelastic phenomena occurs, which could be highly nonlinear. So with this, we want to use some numerical example to demonstrate the feasibility and the robustness of this real-time aerodynamics hybrid simulation methodology. We used first example, we used the rigid sectional model of a long span cable supported bridge. This is the numerical structure parameters. Here is the physical fluid. We used both linear and nonlinear window models in our investigation. And so these are the structural parameters in the scaled sense, because we have a scale ratio from the prototype structure to the model in the wind tunnel. And this is the parameters for the electromagnetic actuator we selected to use. And these are the linear wind force and nonlinear wind force time history. As we can see, if we have a linear wind force and the real-time aerodynamics hybrid simulation result, actually, this is zooming in figure for the time history, actually present excellent results. The same conclusion also can be observed for the nonlinear wind force. As you can see, there's they have almost exact the same with the reference displacement. So now we understand the real-time aerodynamics hybrid simulation. The concept, the essential idea is, as long as we put the scheme in the wind tunnel, and all the members, components, and even the energy dissipation devices enveloped or enclosed by the scheme can be put in the computer numerical world. So with this consideration, we also tried another example. That's the base pivoted tall building with a full-scale TMD. So here the unique feature is that because we want to use a full-scale damper, and so the experimental component and the numerical world, they have different scales. So we need to add some scaling conversion schemes for this situation. And these are the building model parameters in the wind tunnel. And so this is the overview. So here is we use the two actuator to represent the damper force. And as we can see, the real-time aerodynamics hybrid simulation give us excellent results in this numerical example. And also we can see if we put the TMD, actually the mitigation of the crosswind direction response is very obvious. So in addition to this real-time aerodynamics hybrid simulation, we also developed several machine learning-based tools to further enhance our cyber-physical system for wind engineering application. One tool is in this hybrid system, we know if our structure becomes complex and go to strong nonlinear, and then probably even though with this design control, the integration scheme is not that important, but we cannot have that long time simulation, right? So we need it fast enough. And for this purpose, we develop a so-called knowledge enhanced deep learning for wind-induced nonlinear structure dynamics. So we can put it in the computer. It's very fast. The unique feature here is compared to the conventional deep learning, we have purely rely on the data input output to train the model. We also take advantage of the knowledge, including the physics knowledge. That's for example, the governing equation, and also the empirical knowledge in terms of semi-empirical equation or empirical equation, and also even for incorporating the equation-free knowledge. But here, this is not the focus for today's presentation, so I will not go that far. But we can show the results. As you can say, once we incorporate the knowledge, the data efficiency has been significantly improved, and also the robustness of the model has been greatly improved once we incorporate all those knowledges. And the other thing is, once this test has been done, if we realize the structural response is too large, we want to do the aerodynamic mitigation or aerodynamic shape optimization. So we want to do the shape optimization to efficiently do this. We develop a so-called knowledge enhanced reinforcement learning, because reinforcement learning has self-evolution feature. And with this scheme, we can say the optimizer for aerodynamic mitigation is very quick for convergence compared to the conventional optimization schemes, for example, the PSO or the basic gradient descent method. Okay, so another thing for the last thing today I would like to mention is we also want to enhance our wind tunnel in this cyber-physical system because the current wind tunnel, no matter how large of the wind speed it can generate, usually it generates this kind of we call it stationary wind. But the extreme winds, like the hurricane, downburst, or tornado, they usually present this kind of wind, or we call the non-stationary winds. And so we want our wind tunnel can generate this non-stationary winds because this is very important, because the non-stationary winds not only just change the wind input, but also it will change the mapping rules from the wind to aerodynamic load. we call it the transient aerodynamics. So for this purpose, we developed this like a multiple fan active control wind tunnel at UB, and to effectively simulate those transient wind in the wind tunnel, we used the deeper reinforcement learning based control system to equip this wind tunnel, and the result is pretty promising. You can see that's the this is a numeric example, by the way. Currently, this is the wind profile we generated, and those profiles are different with the power law or log law conventional wind profile described in the code and standards. And this is the transient wind time history we generated. And so the implementation of this control system, the algorithm is on the way, although a little bit slow due to the pandemic situation. So with that, I would like to thank my collaborator, my colleague at UB, Professor Siva, and also Professor Wei Song at the University of Alabama, and my former students, Professor Reda Snakey, and also, of course, my PhD students. Thank you, and I welcome any questions if we have time. Emma, I should stop sharing the screen, right?
No, we can have few questions. Any question from the audience? I see, okay, first question came in here. How well can a CFD model capture all the extreme surface pressure or extreme loading on a surface? What are the major challenges using CFD and the fluid structure interaction research besides computational time? I don't know the name of the who sent the question because it shows as a number.
Yeah, this CFD, as I mean mentioned, apart from the computational demand we have, we need the issue here is first, even for CFD, you need a validation. So you still need to go to, unfortunately, go to experiment because currently in the wind energy community, the full scale data is so small, little. Of course, now it's more and more, but we still need to rely on the wind tunnel. The second is there is in the modeling, there is a turbulence closure, and we probably need to use the LES or at least the DES to capture those fluctuations. If you just use the range, you just get the mean value. That's not that useful for dynamic analysis. Hopefully my response, my answer, answer the question.
Yeah, I have another question about the validation. You compared like the displacement with a reference displacement, like the displacement from the hybrid system to a reference displacement. So can you elaborate like what is this reference displacement, or how did you validate your model basically?
Oh, that part, I mean, the comparison part is with the numerical model, because we assume there's no hybrid, everything is similar as usual in the numerical world. And the other is we put some like actuator and used this and the controller used this methodology. And we didn't implement the comparison is not the physical world, because we didn't implement that one, although we plan to. We got the budget and to do the test in at the FIU, but a little bit delayed again because of the current situation.
Yeah, I understand. Yeah. My other question is actually, we raised that point yesterday in our presentation about the repeatability of this kind of testing. So how did you consider or quantify the variation in the forcing function or when the pressures over the surface of your rigid model?
You mean how to quantify what?
The uncertainties in the when the pressures or the wind forces acting on your model, basically, because to repeat the test, and then the input in your numerical model is something that you predefine it in the experiment.
Mhm.
So how do you make this change in the real time between the actual wind forces acting on the model in the real time compared to the predefined wind loads in your numerical model?
Yes, I think if I understand your question correctly, there are a number of uncertainty source here. I mean, if we put here in the wind tunnel, I mean, this one is the aerodynamic force here. There are some uncertainty here because if you want to repeat this one, you will never be able to get the exact same one, right? That's the uncertainty here. So this one is the motion is from the numerical model, the structure dynamics, and we use through actuator we put on the scheme. This is also another uncertainty there because you actually in the modeling of your structure, you also including the uncertainty because that's not you don't have, you not necessarily have all the information. But I would say the if we design experiment like this way, it's kind of we are in the computational domain, in the time domain, sorry, in the time domain. So in the time domain, the only way you quantify your uncertainty is you kind of do like very naive and test. You do multiple tests to do this because each realization. Of course, if all those ones is in the Gaussian distribution, this is another story.
Yeah, thank you. I think we have one last question from Dr. Ashrafi. He's asking how you generate and validate your non-stationary wind input.
The non-stationary wind input, how do you validate that?
First, how did you generate it and how did you validate it? Yes.
That's the, I think the last slides, right? So because we have a kind of a unique wind tunnel system here, we have 64 fans, individual control. So we can by control the fan speed and the different fan arrangements, and we can generate those wind, the non-stationary wind or transient wind. So that's the capacity of this device at UV. The second is how to validate it is that's pretty straightforward because we always have a target. So we just compare to the target because in the wind tunnel, what kind of wind we want to generate, we tell the wind tunnel is our input. And this target is from the our understanding of all those extreme wind system based on the full measurement data or the meteorological knowledge on this. So once we have this, our target, we put it in the, we tell the wind tunnel and the wind tunnel will generate the signal and we compare the signal generated and the target. That's the basic validation.
Yep, sounds great. I think we don't have more time for more questions. If you have questions, please feel free to email Dr. Wu. Dr. Wu, thank you very, very much. A very informative presentation. We appreciate your time.